Hello students, welcome back. Today we are going to talk about something very powerful in calculus, the definite integral. We've already seen indefinite integrals, which give us a family of functions. But here's the catch. When we want an exact numerical value, like the precise area under a curve between 2 points, we need definite integrals. Think of it like this. Indefinite integral gives you a general recipe with a constant, while definite integral gives you the final cooked dish, one single number. A definite integral is written as integral from a to b of f of x dx. Here, a is called the lower limit and b is the upper limit of integration. For example, integral from 0 to 1 of x squared dx. The function is x squared, lower limit is 0, upper limit is 1. This notation is compact, but it's telling us we are capturing the area under the curve y equals f of x between x equals a and x equals b. Now, how do we calculate this definite integral? If capital F of x is any antiderivative of f of x, then the formula is integral from a to b of f of x dx equals capital F of b minus capital F of a. This is known as the fundamental theorem of calculus. So instead of summing infinitely many small slices, we just evaluate the antiderivative at the two endpoints and subtract. Isn't that elegant? Let's see the geometric meaning. When we plot the graph of y equals f of x, the definite integral from a to b represents the signed area under the curve. If the curve is above the x-axis, the area counts as positive. If it is below the x-axis, the area counts as negative. So, the total definite integral is like positive area minus negative area. For non-negative functions, it simply gives us the actual geometric area. That's why definite integrals are so useful in physics, economics, and engineering whenever we want precise accumulation. Let's solve an example together. Evaluate integral from 0 to pi of sin x dx. Step 1. Antiderivative of sin x is negative cos x. Step 2. Apply the formula. So, integral from 0 to pi of sin x dx equals capital F of pi minus capital F of 0. That is, negative cos pi minus negative cos 0. Now cos pi equals minus 1, so negative cos pi equals 1. Cos 0 equals 1, so negative cos 0 equals minus 1. Subtract 1 minus bracket minus 1 bracket equals 2. So the exact value of this definite integral is 2. Geometrically, it's the area under one arch of the sine curve from 0 to pi. So students, let's quickly recap. Definite integrals give us exact numerical values, unlike indefinite integrals that give families of functions. We write them with limits integral from a to b of f of x dx. The formula is simple, capital F of b minus capital F of a. They also follow properties like linearity, reversal of limits, and additivity. And geometrically, they represent the signed area under the curve. Definite integrals are everywhere, calculating distance traveled, work done by a force, probability in statistics, and so much more. And that's the foundation of definite integrals. In the next video, we'll explore how to use these integrals to evaluate even more complex functions and applications.